Hello. We continue our lessons of integration. Now, you remember in our first lesson of integration that we said that this was the fundamental theorem that is the theorem or the one to have really made a breakthrough in the science of calculus. Before that, scientists used to calculate areas under the graph by summing up small pieces of rectangles, for example, which was very tedious exercise. The fundamental theorem also was successful in proving that differentiation and integration are really the converse operations to one another. Now, in our first lesson of integration, we mentioned also Newton's proof. What we did, Newton actually, in order to calculate the area under a continuous graph, what he did, he started, for example, from the point A till another point X, and this becomes, therefore, the area as a function of x, and A coincides to the initial conditions, which is really also coincides with your arbitrary constants. So what he did, he proved that d of x by dx is equal to small f of x, which is here, this is the graph, the function coinciding to this graph. Now, from this, you can directly obtain that a of x is equal to the integral from a to x of f of t dt. Now, from this piece of information here, which Newton arrived at, you can either actually what you do. Usually people write this in the form of capital F of x plus c, where f is the antiderivative of the small f. Now from here you can directly obtain the fundamental theorem of Newton and Leibniz. How is that? You can substitute x is equal to a. So what you get, this becomes equal to 0. This cancels out. And here you get here, if this is, in other words, if this integral is from a to a, it cancels out. And you get here f of a plus c, which means that c is equal to minus f of a. In other words, now we arrived at the fundamental theorem is that the integral from a to x of f of t dt becomes equal to capital F of x, which is where f is the antiderivative of small f minus f of a. And this is the theorem of Newton of Leibniz, which I said that made a contribution, or really the breakthrough in calculus, because before that the integration was a very tedious exercise. Now this expression on the left-hand side now constitutes an indefinite integral because it's a function of x. In other words, it's the area under the graph from a point A till the point x, and x moves in the interval from A to B, for example. And here, when you differentiate this, you differentiate capital F of x, which gives you small f. So at the same time, it constitutes an area, and at the same time, it's an antiderivative of small f. But then there is here a major drawback. The drawback is that the f has to be continuous, and or at least having an antiderivative, and this actually is the major drawback of the fundamental theorem. So from there on, Riemann intervened with his approach to the definite integral, and this is actually the subject of this lesson. Now, what will be speaking about is the new definition of the definite integral, and we shall be focusing first on the how the fundamental theorem is violated, why, and then the case of continuous functions, which is the special case of the Riemann sum, and then the Riemann sum and the idea of the Riemann sum, which was the key to approach the concept of the limit integral. And finally, the conditions of integrability of functions. Now, why the definite integral is another thing than antiderivative? Because the area here again is the fundamental theorem. It tells you that if you want to calculate the area under a continuous curve, then what you calculate the difference between the antiderivative between the limits of integration a and b, and then if the area is equal under the graph y is equal to f of x is equal directly to the capital F of b minus f of a, where capital F is the antiderivative of small f. And this is the fundamental theorem that was discovered in the early 18th century, and this is the way how people used to calculate area under curves, but these curves have to be related to graphs of functions that are continuous. Now, the theorem, as I said, is only valid for a class of functions like the continuous ones, or having antiderivative. And this is an extension that Cauchy made, not necessarily, because a function, if it's continuous, it has an antiderivative, but it's not necessarily continuous to have an antiderivative, and therefore it's enough, it is sufficient but not necessary. So you may do some extension on the fundamental theorem. In other words, it may not necessarily be continuous, only it is sufficient that it has an antiderivative. So if you want to calculate the area under the closed interval AV, then what you do is that you apply this fundamental theorem, but scientists discovered that there are other functions that are not continuous, or they may not have an antiderivative, and still they have a definite integral. And from this point on, that these functions are, as I said, the science or the concept of the definite integral was born starting from this instant, or that the scientists discovered that antiderivatives are not really integrals, and there on the Riemann integral was born. Now the Riemann integral, why it was born? Because, as I said, scientists discovered that there are functions that do not have an antiderivative or are not continuous and still are integrable in the sense of Riemann. For example, this function here, this function is not continuous, of course, because it has a jump, a discontinuity, as you said. You remember our lesson of continuity, so it is not continuous, and at the same time it has no antiderivative because it does not comply to a theorem saying that if f is differentiable, f dash must comply with the intermediate value theorem, and this does not on this closed interval, and therefore this function here has no antiderivative in any interval containing the origin, and yet it is integrable on any interval containing the origin. So here again we see now that functions may be integrable and yet may not possess an antiderivative or may not be continuous. And from there on now we have to define the meaning of the definite integral. Now, first of all, we have to consider the case of continuous function, because from the case of continuous function, which is the simplest, we move on to the definite integral as a general concept later on. Now, for example, if you wish to calculate the area under the continuous curve, for example, you consider the simple continuous curve y is equal to 6c minus x squared, which is a parabola open from below, and you wish to calculate the area under the graph from 0 to 4. What you do is that you start summing up area of rectangles, like we did before. You subdivide the base into n, for example, subdivisions, and you keep on calculating the area of these small rectangles one by one. For example, here, this is your parabola here, open from below, and you wish to calculate the area under the graph. What you do, for example, you take some 4 points, for example. Each one is the middle of each interval. You have here 4 sub-intervals. For example, you multiply, for example, the base, which is 1 times the height, which is f at 0.5. You substitute 0.5 in 16 minus x squared. So you have here the sum of these heights here, 4 heights. You multiply them by the base, and you get the area almost equal to 43. Now, the area, the exact area, you have to calculate it. You can calculate using the fundamental theorem because this is a continuous function. So we found that it's not exactly, there is an accuracy or an error of 0.8%. Now, if you increase your subdivisions, if you double them, in other words, if you take instead of 4 heights, you take 8, for example, you take 3 points in each small subdivision, and then the end point, and you keep doing this, proceeding like this, so you have now 8 points instead of 4. Now, of course, since you increase the number of subdivisions, then you have a better representation of each smaller area. In other words, it approaches to the exact integral or the area under the graph. So when you do this, you realize that the area here becomes, you have a better precision of or an error only of 0.2%. So to calculate the area using the old method, as we said, you divide the interval from 0 to 4 into n subdivisions, each of length 4 over n, because this is equal to 4, length is equal to 4. You subdivide into n sub-interval, and then the area lies in which case between the two upper and lower upper value of which are the outer rectangles here. As we saw before, you have a set of upper rectangles and a set of lower rectangles, and you can actually, what you do is that Here are they. Now again, here you can, instead of taking, before we took them as rectangles, it doesn't matter whether rectangles or they are trapezoids or like we saw previously, or small rectangles here. Here are, we call these inner rectangles because they are below the graph. In other words, the area of these rectangles, when they are summed up, the area becomes equal, is little bit less than the area under the graph, whereas here the area of the rectangles, the sum of these areas are higher than the area of the graph, but doesn't matter. Now you have here, the area is enclosed, your exact area is enclosed between these two, the upper bound or the upper limit, or you can say the upper sum, and here this is the upper sum and this is the lower sum of these rectangles, and the exact area lies between these two limits. So if these two limits, the inner and outer rectangles as areas, tend to 1 when you increase this number of subdivisions, now what would happen, both coincide, or they approach each other. And since from the Squeeze theorem we saw in our lesson of limit, since both tend, if they both tend to one limit, then what's in between must tend to the same limits. So what we did, we have to use some series because the idea is that you sum up the area of these rectangles. How would you do this? You multiply each height by the base. So you have an equal base, all of them, because you have equal subdivisions. You have 4 divided by n, and then you sum up these heights together. When you sum up the areas of the inner rectangles, you obtain the lower value of Sn, whereas when the upper limit or the upper values of areas of these outer rectangles, these are the areas of the outer rectangles, and these are the area of the lower rectangles. And then what you do, you have to rely on series which are finite series, the one that we saw before in our introductory lessons. We said that series in the past were finite series. Here we have a number of n subdivisions, so they are finite. So we add up these heights together and we come up to, here are they, like the same method that was performed by Archimedes. You have here a sum of n, you have a series of n terms, whether the power is 1 or 2, etc., depending on the curve. If your curve is a straight line, you end up with, you have to use this one. Whether if you have a parabola, then you have to use this one. And you come up then to the first, this is the upper, this is the area of the outer, of the inner rectangle. This is the area of the sum of the inner rectangles constituting each of base equal to 4 over n, whereas here this is the sum of the areas of the outer rectangles, again constructed on the same base, which is 4 subdivided into 4 over n small pieces. When you add up the outer rectangles and the inner rectangles, you have these two expressions, and then it means that your area is enclosed between these two. Here directly we see that when you take the limit here of n, when n tends to infinity, you end up with what? That you have the area becomes 128 divided by 3. Actually, we can show this on here, a small applet. Here we see that here is your graph, y is equal to 16 minus x squared. And here we started by choosing inner rectangles. You have here 4, but you can increase them, of course. You can increase the number of inner rectangles. And you may take outer rectangles. It doesn't matter. Because as long as you increase the number of subdivisions, here you realize that you remark that the exact area, the real area is 42.6. Whereas the area of these rectangles, the outer one is 45.75, whereas the inner one is 39.6. And the more you take number of subdivisions, you approach the exact area. Here they approach each other. You see that they approach each other, and as the number of subdivisions goes to infinity, you end up with the exact area, which is you can use the fundamental theorem in this case, or in other words, both of these sums, whether the outer one and the inner one, they approach the value of 128 over 3. So we see now using the these using the squeeze theorem here, that here this is the area of the inner area, the sum of the inner rectangles, and this is the sum of the outer rectangles. And when you take the limit when n tends to infinity, you find that both they approach the value 128/3, and from here you see that now we obtain the exact definite integral, which is the area under the continuous curve y is equal to f of x. Now, so we come up to this theorem. If f is positive continuous function in the closed interval AB, and you have the lower and upper areas of rectangles, which are the sums of the inner outer rectangles, then the two limits, if you take the limit of both of them and this limit exists, and they are equal, then what you have is the area, because actually it has been proved that these two limits, in fact, they exist since the function is continuous, and the limit will give you the area exactly of, because they both coincide together, and therefore A, which is the exact area, coincides to this limit, and you can directly calculate the area under the graph. Now we start to speak about releasing the conditions imposed by the fundamental theorem. Now, not only that, but even doing calculating area using partitions, as we done here, these process of partitioning the area into small rectangles was known in the past, as a matter of fact, since the ancient times, except that they were considering continuous curve only, and at the same time they were considering an equal number of subdivisions. In other words, the subdivisions are equal. So we have to release, and that's the idea which Riemann did, is that he started by releasing these conditions one by one. So instead, for example, of taking the maximum value of f, add the minimum value of f, in other words, seeking to calculate s upper and s lower using the upper value of the function inside these small partitions, you can take any value t, any point t inside these partitions. For example, in the first partition, we said that all of them, considering, for example, this particular example, all of them were having equal partition, 4/n, and when we calculated the upper S upper, which is the area of the outer rectangles, we considered on each small partition, we considering multiplying the base, the length of each subdivision times the height of the function, and we consider taking the upper value or the maximum value of the function. So, for example, at the point C or a minimum value at point D. This is what we did, in fact. But it's not necessarily that you multiply the base delta x times the height f of at C or D, what is likely what we did in this example. You can take any point t, j inside each subinterval from the point xj minus 1 till the point xj. So this is the first release here. Here, as we did, for example, if we want to calculate, this is one partition from xj minus 1 to xj. What we did in order to calculate the area of this small partition, we're considering the outer rectangle by taking the maximum value of the function at this particular, in this small subdivision, or for the inner rectangles, the lower or the minimum value. But we can take, in fact, any point tj such that f of tj is less than the maximum value of the function or the minimum value of the function. It's irrelevant. So if we allow for equal subdivisions in the interval AB, and again, we keep the same condition of equal subdivisions, n equal subdivisions, and so delta x now become equal to xj minus xj minus 1. In other words, all the delta x's are equal, but tj here, it's any point in the interval from xj minus 1 to xj. And what we do is that we end up to a form like this. Still, the area, the sum of your area becomes equal to what? Becomes equal to the base, which is delta x, they are equal subdivisions, times the height. Here the height is chosen at any point tj in the closed interval between xj and xj minus 1. Still, now you can realize directly that again this is less than s upper, the upper areas, the area of the upper, the outer rectangles, and this is the area of the inner rectangles. And again, since these both areas or these both sums tend to the same limit, so again we are safe, and your integral here or your sum here tends to the same limit where n tends to infinity. So each of these S upper and S lower of n tends to a limit S, then the sum tends to the same limit, giving the area under the continuous curve. So this is the first, we have released the first condition of calculating area through subdivisions like we did. And we have released the first condition that we do not have to take the maximum value or the minimum value to substitute into the expression for calculating areas, and we may take any point Tj in this subinterval, but we kept actually the conditions of equal subdivision. So this is the first thing we did. Now the area, the sum must tend to the same limit based upon the Squeeze theorem. As we said, irrespective of the choice of Tj inside each subinterval. But then Riemann generalized this result further. What he did is that not only he took equal subdivision, but he can actually release also this condition by taking unequal subdivisions. For example, he may choose x naught, x1, x2, such that x1 minus x naught is not necessarily equal to x2 minus x1. In other words, he take any kind of partitions of the base of the closed interval from A to B. And this rule is called a partition. He chose a particular partition. He called this a special partition or a chosen partition. And the maximum among these partitions, he called it the norm of the partition. So he started first to subdivide the interval from A to B into unequal partitions. Each one is equal to delta xj, and delta xj from j from 1 to n are unequal. And you take also, as we said before, because we kept the same release of the first condition that we imposed, that we have to take the upper or lower, the maximum or lower value of f. Again, we kept the same choice of not only of partition, but of course of taking of Tj any point in each subinterval to substitute for into the sum of our rectangles. So here again he partitioned the base into n subintervals, but these n subintervals are not necessarily equal. And what he called the norm of the partition, the maximum length, in other words, the difference between x1, x0, or x2 and x1, the maximum one, he called it the norm of the partition. And when this norm of the partition, of course, tends to 0, it means that all the partitions tend to 0, and then the limit becomes equal to your definite integral. So here now is born the Riemann sum and the integral and the definite integral. So now we have to calculate the sum of these rectangles, but what we did, we released few conditions. One of them is that it's not necessary to take the maximum and the minimum value of the function in each partition. Again, the length of each partition again is not necessarily, they're not being necessarily equal. If you do this, then you end up with what is called the Riemann sum. So the Riemann sum of a function f is, which is the base of calculating the double integral. You have a closed interval AB, and what you do is that you sum up the area of these rectangles, and you notice here directly this expression here that all the partitions or the sub-intervals are not necessarily equal, and again you may not substitute for x the maximum or minimum value of the function. You may take any value Tj inside each sub-interval. And when you sum up all these areas together, you end up with what is called the Riemann sum. Now, if this Riemann sum exists, and if this Riemann sum, when you take the limit, exists, then tends to a finite limit, then you call this the definite integral. So here again, not only Riemann notice that not only you may release the condition of equal subintervals, or you take the maximum or minimum value of each of the function inside this each subinterval, but you may also allow for more choice. You may, for example, allow f to be discontinuous on the interval AB. This is one choice that you can do. And you can have periods or subintervals inside the AB in which the function may be negative, or the value of f of x may be negative or positive. In other words, you have different choices. You don't have to restrict yourself to that the function be positive, like the previous theorem that we saw, or the function to be continuous. It may be discontinuous. Again, the distance, as we as you have seen before, between xj and xj minus 1 can differ for each j. And again, tj, as we've seen, can be a point, any point inside each subinterval. So you have here different choices of your f. So long as your Riemann integral, your Riemann sum exists, and not necessarily complying with any previous or chosen or a certain particular choice that you choose, you may allow for different freedom of choice of your function. Your function may be discontinuous, may be positive or negative in the interval. In order to calculate the area of these small rectangles, you may take for each sub partition you may take different base distance of different bases or different lengths of each partition or each subintervals, and you may also take values of the function which may not be necessarily the maximum or minimum. And when you do that, so long as your Riemann sum exists and its limit exists, then now you can say that your integral exists. So now we come to the definition of the definite integral. If S is defined in a closed interval AB, the definite integral of f from A to B is equal to this limit. If this limit exists, this is the Riemann sum, allowing for different freedom of choice of your function. If this limit exists, as the norm of the partition tends to 0, in other words, all the number of subdivisions tends to infinity. If this exists, then here now the definite integral is born. So the definition of the integral, of the definite integral now, of the function f from A to B, is in fact the limit of the Riemann sum. And in which case f is called integrable, and A on the interval, on the closed interval AB. So A and B are called the limits of integration. A is the upper limit and B the lower limit. F is the integrand, d of x the element of integration, and finally this sign notation here is the previous notation of Leibniz. But again here you have a function which is may not be continuous, may not have an antiderivative, may not be positive or may not be negative. You have a list of set of choices which you can allow f to be adhering to, and yet since the limit of your Riemann sum exists, then your definite integral now exists, and the function is called Riemann integrable. Again here you can actually do the same thing. This is called an upper Riemann sum and lower Riemann sum, the same idea we did before, except that instead of taking f of tj, you can take again the maximum in each subinterval and the smallest value of the function, but we can allow for you can allow for different partitions. They resemble S upper and S lower, except that the partitions are not, you don't have an equal partitions, but it resembles the first slides we have been explaining, and these are called the upper lower sum and the upper and lower Riemann sum. In fact, we can show this. This is this is a mathematician of the 9th century who is called Alhazen, and this mathematician followed the same example of Archimedes, and he almost discovered the upper and lower sum of Riemann, except that his function was continuous, because I said before, all these mathematicians of the ancient times were not supposed to consider functions that are not discontinuous, because all the phenomena are continuous, and therefore he applied the same idea of summing up rectangles, but here he was considering the volume and not the area. So what he did, he wanted to calculate the area of the volume of rotating a parabola around this axis here. So what he did, actually, he this is his area here. This is his region. So he subdivided into small lamina, horizontal lamina, and then he summed up. He made each lamina rotate around around this axis here, and you directly notice here that the volume of these small cylinders are inner cylinders. But if you take also the outer cylinders, you may end up with the same result, in that what you take the limit of these cylinder, the volume of these cylinders, you end up with this volume here. So the idea is the same. In other words, these are the old methods until to calculate whether areas or volumes until Newton and Leibniz discovered the fundamental theorem, except that there is a drawback, is that this result or this theorem applies to continuous functions, and then so it just appears that it's not necessary, and therefore the Riemann integral was more general because he considers only functions that may not be continuous. Now, as I said, these represent the outer and inner rectangles according to the partition rule P. For example, here we have an integral of square root of x, and we take a different partition. This is direct applications of this sum. Sometimes it's called Darboux sum or the upper and lower Riemann sum. You have here a period from 0 to 1, and you partition it, but not in equal partitions. Here, this is the norm of the partition. Of course, what you do is that you do the same thing exactly. Here is your area. And you partition into unequal. You have here unequal partitions. What you do is that the length of the J's partition, you partition according to the rule. The first point is 1 over n squared. The second one is 2 over n squared, etc. So you have unequal partitions. Here the norm of each partition, or the length of each partition. Now the maximum would be, of course, at the end, and it would be equal to 2n minus 1 divided by n squared. So what you do, you multiply each height. Here you may choose for ease, you may choose the maximum value of the function or the minimum value, and you end up with this is the upper Riemann sum and this is the lower Riemann sum. Here you have unequal partitions, each one of length 2j minus 1 divided by n squared at the particular point xj, and this is the value of the function. Here you have the maximum value, and here you have the minimum value because you multiply by the 2j minus 1. Here you sum up from 0, and here you sum up from 1, and you realize directly that when you add up these sigma j square and sigma j, you have to rely on the sum of finite series. So this is the upper Riemann sum and this is the lower Riemann sum, and when you take the limit when n tends to infinity, you realize directly that the sum tends to 2 over 3. Here you want to calculate the integral from 0 to 2 to f of x dx. Here you realize that the function here, your function is discontinuous. At the point 0, it's equal to 0. You want to calculate the upper Riemann sum and the lower Riemann sum. It's easy. Why? Because the function takes the value of 1 all the time, except in the first subinterval, which is if you divide by from 0 to 2, this interval from 0 to 2 into n equal subdivisions, each of 2 over n. So you only realize that the first sub-interval only has a maximum value of 1 and the minimum value of 0. Otherwise, all the intervals, the area of the rectangles, the others are equal, whether you the inner ones or the outer ones, because you have an equal value of 1. So here you have so you subdivide the interval from 0 to 2 into n equal subdivisions, of course, for ease, and then you multiply what? You multiply the value of the function, the height times the base. Here you have the first, the problem occurs at the first subdivision. So the upper Riemann sum becomes equal to 2, whereas in the lower Riemann sum, you have here all of the subdivisions have same height 1, except the first one, the value is equal to 0. So you end up with this lower Riemann sum, and when you take the limit when n tends to infinity, you end up with 2. It means that your integral here is the definite integral is equal to 2. Now you cannot use the fundamental theorem to tackle a problem of this one because your function was not continuous. So here you see that the integral, this is the definite integral, and the result is equal to 2. So now we come to the condition of integrability. What are the conditions that the function is Riemann integrable? So first of all, we have to say that the existence of the definite integral depends on the existence of the limit to Riemann sum. In other words, we started by defining the Riemann sum, and then we took the limit. If the limit of the Riemann sum exists when n, the norm of the partition, tends to 0, or the number of subdivisions tend to infinity, then the limit exists and the Riemann integral exists. So when is the limit? This limit exists. First of all, if f is continuous in AB, then it is integrable on AB, on it. Of course, you don't need to use Riemann integral here to calculate the integral. In other words, most of our applications are you can apply the fundamental theorem. You only apply Riemann when you cannot apply the fundamental theorem. So if f is continuous, of course, it's Riemann integrable. Again, if f is bounded in AB, then it's continuous, and continuous except at finite number of discontinuities. It's called sectionally continuous function, then it is integrable. And the third condition, if f is unbounded, of course, then it is not integrable on it. For example, you have here a function here. This function is has three rules. For x less than 0, it's 1 plus x. For x from 0 to 2, you have 2 minus x, etc. And you wish to calculate the integral from minus 3 to 1. Of course, this function is not. Of course, you can apply the fundamental theorem. As a matter of fact, how we shall see this when we come to exemplifying different situations in which you can apply the fundamental theorem. But we wish to do this through Riemann sum. Can would this function be integrable in the sense of Riemann? Of course. Why? Because this function is continuous except at finite number of discontinuities. Here you have 2 points of discontinuities as 0 and 2, and therefore you can apply the Riemann sum here. What you do is you can sum up here the area of this piece, this triangle, plus the area of this triangle, plus the area of this triangle here. Direct. I mean, you don't need to do partitions, because these are, of course, you can partition. You can partition here, except that you don't have to. Why? Because there are some of small areas which you know, because they are either rectangles or they are small triangles. So you can apply directly your sum, your knowledge of area of these particular figures here, shapes here. They are. This is a triangle, so the area is equal to 1, the base times the height, which is half. And then you sum up here the area of this other triangle, which is 2 times 2 times half. And then the area here, which is 3 over 2 times 1. And you get, at the end, the area is equal to 4. So like this, we come to the end of this lesson here. And it's important because this lesson sets up the idea of the definite integral. We've seen how the evolution of calculus began. It began with the crude ways of calculating areas by using the exhaustion principle, for example, of Eudoxus, in which Archimedes used it to square the parabola. In other words, to calculate the area inside a parabola. And we have seen that starting from Archimedes, since the 17th century, almost people used to calculate areas under the graphs by subdividing or dividing the inside area into small rectangles or trapezoid, and then summing these areas up. Whereas this is a very tedious and difficult way of doing it, because you have to rely on series and finite series, and then you take the limit, etc. It was known, actually. The idea of limit itself was only born in the late 18th century by Cauchy, etc., and Bolzano. But still, they increased the number of areas, or the number of subdivisions, to approximate almost the area. And then came the Fundamental Theorem in the early 18th century by Newton and Leibniz, and actually that was the real breakthrough, because it proved that you can use the antiderivative of a function, and Newton called it the method of inverse tangents, in order to calculate areas. The only and then, of course, as we said before, that Cauchy extended this theorem, but in any case, it has a major drawback. The major drawback of this theorem is that it cannot deal with functions that are not continuous or not having an antiderivatives, and we had to wait another century almost, because in the beginning of the almost a century and a half, until Riemann defined the concept and the general concept of integrability, and away from antiderivative. And it just now we discovered that definite integrals or that antiderivatives are really, they are not integrals, and the definite integral has to be based on a clear cut knowledge of a certain sum. And this sum, it differs from the ancient times, in that the ancient times the functions were continuous, but here you can deal with functions with all sorts of discontinuities, or of all sorts of peculiar properties, and still, if this Riemann sum exists and its limit when you take the norm of the partition tends to infinity, if this limit exists, and therefore we can now base we have arrived at a real clear-cut view of what is called the definite integral. And with this, we come up to the end of this lesson, and I wish you understood the concept of integrability. And I wish to remind you again, like in every lesson, that all these lessons are uploaded to the site of the Untitled University. And until we meet again, I wish you good luck, and I thank you for your attention.